This is section 7.6 Millikan's oil drop experiment, and we're going back to the early 1900s when physicists knew that atoms were made up of fundamental charges. And we're going to be looking at this case at Millikan and what his experiment sought to do. Millikan's testable question, or what he was looking to do, and this was what many physicists were doing, was how could you figure out the charge of an electron? That was the testable question that we were looking at. And what Millikan did was he devised this experiment to calculate it. And he was taking two plates separated by some distance d, so a positive end and a negative end of the plate, and he was putting a fine mist of oil, shooting it through these charged plates. Oil mist, and he was looking at each specific oil drops. So what was going on in this case was he had essentially created an electric field. And he was testing these at different field strengths. Why was he doing these different field strengths? What was the purpose for devising an experiment that varied the field strength? What his goal was in this case, between the negative plate and the positive plate, was to find a time when the oil drop would not gravitate towards the positive plate or the negative plate. He was looking for a case where the oil drop remained motionless. It was stationary between the two plates. And this would be separated by some distance delta D. Well, what's the purpose of having this at a motionless state? He realized that when it's in a motionless state, that the force of the electric force magnitude would be equal to the force of gravity, which would really help him determine this electric field strength. So what Millikan did was he adjusted these different field strengths to see when this would occur. He collected data and had the mass of the object and the voltage across the plates to create this electric field. And he would get it in such a way that the electric force would be equal to the gravitational force, which we know how to calculate both quite easily. The electric force is Q multiplied by E is equal to mg. And this, we're going to say, is our elementary charge, the charge of the electron. We know that we can calculate QE quite easily. That would be Q multiplied by our electric potential all over the distance between the plates. We're going to call it delta D now in this case, and that would be equal to mg, the force of gravity. Solving for the elementary charge Q, we found that that would be equal to mg delta D all over that electric potential. And that's just through basic mathematical manipulation. But when it was in this ratio here, this is the amazing thing that Millikan was able to determine. He figured out that when there was one electron, the charge on that would be 1.6 times 10 to the negative 19. And then he was able to determine that two electrons had a charge of 3.2 times 10 to the negative 19. Then he was able to determine the third charge, which is 4.8 times 10 to the negative 19, etc. He was able to determine that 14 electrons had a charge of 2.4 times 10 to the negative 18. And the really awesome thing about this in the early 1900s was to derive these numbers here. The only way that he was able to was through technology. But think about the technology in the early 1900s. That means the only thing that he had to calculate this was paper and pencil. Calculated all of these by himself with the paper and pencil. And this here gave us another equation. The fact that Q, our elementary charge, was equal to NE, where N is the excess electrons and E was our elementary charge of one electron, in this case 1.6 times 10 to the negative 19 coulombs. Simply amazing on what Millikan was able to do at such an early time. And just for the sake of argument, as usual, let us look at a few examples, like a case where if we have a charge on a small sphere with an excess of 4.8 times 10 to 12 electrons, what's the charge? In this case, it's relatively easy because number of excess electrons n is 4.8 times 10 to the 12. Our elementary charge, because we're dealing with electrons in this case, negative 1.6 times 10 to the negative 19 coulombs. Let us calculate what Q would be. So 4.8 times 10 to the 12th multiplied by the elementary charge. And that is 7.68 times 10 to the negative 7. And in this case, to two significant digits, 7.7 times 10 to the negative 7 coulombs. A very basic problem that we might have to do sometime. If we look at the second problem that I have for you, an oil drop at that mass, and this is going in between a Millikan apparatus. And it's balanced between the two plates, and the charge between the two, potential difference is 250 volts. And we're told here that the upper plate is positive. What does this really mean? If our upper plate is positive, that means the field lines will move to the negative. So field lines move from the negative from the positive charge to the negative charge. And the protons travel in the same direction as the field lines. Which that means our electrons will travel in the opposite direction, so electrons will travel towards the positive end. What that tells us is that electric force is moving towards the positive as well. Therefore, if it's moving towards the positive, that means the charge on the sphere, by the law of electric charges, and it's traveling towards the positive, has a negative charge. And that's huge for part of this question here. So, we're first asked to calculate the charge on the drop. Since we're given the mass, the distance between the plates, remember 1.9 centimeters, always make sure you convert this to the SI unit by dividing by 100, 0.019 meters, and we have our potential difference. It is quite easy to calculate the charge on that sphere using mg delta d all over delta v and making those substitutions. You would get 2.237 times 10 to the negative 18. And in the question, it gives us two significant digits. So we have 2.2 times 10 to the negative 18 coulombs as the charge on this sphere. The second part of this question, I put A and B just because there was another part asked. Is there an excess or a deficit of electrons? Well, that's easy. The electric force is moving towards the positive end because it's in the opposite direction as the protons. Therefore, it has that negative charge. If it has negative charge, it has an excess. Reason why, just one more thing, we know that this is a negative charge. Force of gravity would be going in the downwards direction, therefore electric force upwards. Protons moving towards the negatives, electrons moving towards the positives, therefore negative charge. So we know that this has a negative charge, so excess electrons, but let us just go one step farther. We know that Q is equal to 2.2 times 10 to the negative 8, and that the elementary charge is 1.6 times 10 to the negative 19 coulombs. How many excess electrons are there? We can calculate that from NE. N is going to be Q divided by E. And that tells us we will have 2.2 times 10 to the negative 18 all over 1.6 times 10 to negative 19. And that's equal to 14. So we have 14 electrons in excess. And that's the basics that we really need to know for Millikan's oil drop experiment.